Okay, so this is called related rates. Related rates means your variable is going to be t, time. So we're going to have, like, we can have dy dt, dz dt. We can even have dx dt, okay, or dw dt. Everything is going to be based on time. Everything changes with respect to time, and that's what we're going to find. We're going to find our related rates, okay, can be applied to real-world problems because everything is changing. So let's start with a nice easy one, which is problem number 2, an example, and they give us x plus 4y is equal to 3. Okay, and in A, they tell us dx dt is equal to 1, and they want you to find dy dt, okay, and when x is equal to 2. Okay, so we're going to take the derivative of this function with respect to time. So it's just like using a chain rule. So back in the day, not too long ago, when we took the derivative of this, okay, derivative of x turned out to be 1. That's because we're taking derivative of x with respect to x, which is 1. Okay, but now we're not going to take the derivative of x with respect to x. We're going to take the derivative of x with respect to t. So when I take the derivative of that, I'm going to get dx dt. That's the derivative of x, plus 4 is just a coefficient, and take the derivative of y, which is my dy dt. And of course, as always, derivative of constant is 0. Okay, now I put in all the information I'm given. Okay, I'm given 1 for that, plus 4, and I have a dy dt is equal to 0. I didn't really need 2. Okay, that's okay. Sometimes you have some information that you don't need to use. So we're solving for dy dt. So my dy dt is going to be negative 1 divided by 4. Okay, and that is it. That is all you do. Okay, so that's an easy one. So let's go on to do more difficult one, like number 4. All right, this is number 4. I'm on page 223. All right, this is x squared plus y squared is equal to 2x. Okay, in part A, they give us dx dt, and they say that's equal to negative 2, and then they want you to find dy dt at x is equal to, when they tell you x comma y is equal to 1 comma 1, that means we want to find that at that particular point. Alright, we're going to do the same thing here. We're going to take the derivative of that function with respect to time. So we're going to use chain rule. So that will be 2x times the derivative of x. But in the past, derivative of x was 1. But now it's not. It is dx dt plus. That is going to be 2y. Okay, in the past we said y prime, but now we're going to call that dy dt is equal to 2 times the derivative of x, which is dx dt. Alright, we're going to plug in everything, all the information that we have. Okay, that means 2 in place of x, we're going to plug in 1, and then in place of dx dt, it's given negative 2, and then plus we have a 2 in place of y, we're going to plug in 1, that's given to us over here, and then dy dt is what we're trying to find, and that's equal to 2 times dx dt, which is negative 2. Alright, let's clean this up. This is a negative 4 plus 2 times dy dt is equal to negative 4. Divide by negative 4, and we get 2 dx dy dt is equal to 1, and that means my dy dt is equal to 1 over 2. That's it. Alright, let's hop, skip, a jump, and let's get to number 8. Okay, this is number 8. I'm still on page 223. Okay, number 8 says they want you to find L, the length be the diagonal of a rectangle. Okay, so whenever they give you information, you want to draw a picture. So let's draw a rectangle, and this is the diagonal of the rectangle. We'll call that L. Okay. Who has lengths of x and y? So we'll call that x, and we'll call that y. Okay. So x and y, and assume the x and y vary with time. Okay. And 8. How are dl dt, dx dt, dy dt related? Well, first of all, okay, this is a rectangle. Okay. So how they want you to find out how this is related. This is y. Okay. So if you look at this right there, this is a right triangle. So we know x squared plus y squared is equal to L squared because that's the hypotenuse. So how are these related? Okay, we're going to take the derivative of this. So dx, I get a 2. I'm going to take the derivative of x squared. I'm going to get a 2x dx dt plus 2y dy dt. And then when I take the derivative of L, I'm going to get 2L dl dt. And that is the relationship between the change in x versus change in y versus change in L, which is the length of diagonal of this rectangle. Okay, in part B, they want you to use this information, and they tell you if x increases at a constant rate of 1/2 foot per second, so that means dx dt is what's changing because x is increasing at 1/2 foot per second. Okay, and then it says y decreases. Okay, y decreases, that means dy dt decreases means it's going to be negative at 1/4 foot per second. They don't tell you it's negative, but you have to put in the negative, 1/4 foot per second. Okay. How fast is the size of the diagonal? So that's L is the size of L is the diagonal. So they want you to find, okay, the change in the diagonal. So dl dt when x is equal to, okay, when x is equal to, let me erase that, when x is equal to, okay, 3 foot and y is equal to 4 feet. Okay. Alright, we already took the derivative of this relationship, so all we have to do is plug in the information. That's all I'm going to do right here. So we're finding dl dt, so that's located right there. So everything else we're going to plug it in. So 2 times x, which is given to us as 3. Okay, you don't have to put the feet in right now. You can put in the feet and the seconds later. If you don't put in feet and seconds, you're in trouble. Okay, so that's x, and then dx dt, which happens to be 1/2. Okay, and then I have a plus 2 times y, okay, and that is 4, okay, and times dy dt, okay, dy dt is negative 1/4, okay, is equal to 2 times L, dl dt. Alright, I don't know what L is, so when x is equal to 3, okay, and this is equal to 4, I do know what L is, and they don't give it to us, but we know what L is. It's 3, 4, 5 right triangle, so L's got to be 5, so I'm going to put in 5 right there. Alright, so this and this reduce, I get 3, plus this and this reduce, I get a negative 2 is equal to 10 dl dt. So this is going to give me dl dt. So when I finish solving that, dl dt turns out to be 1/10, okay, feet per second. So L is changing at 1 feet excuse me, 1/10 of a foot per second, not 1 foot, 1/10 of a foot per second. So it's getting bigger because this is positive. Okay. All right. The second part of the question is the diagonal increasing or decreasing? And then we say it is increasing because dl dt is positive. If it was negative, it would be decreasing. Alright, let's do a couple more problems. Okay. And let's go to number 12. I'm on page 224. Alright, it says the stone is dropped. Okay, we're going to drop a stone. Okay, here's a stone. We're going to drop it. Always draw pictures. Okay. In a still pond, into a still pond, sends out a circular ripple whose radius increases. Okay, so that means you're going to have a ripples, still pond. Okay, it's dropped. You're going to have circular ripples. Okay, and this is my radius r. Okay, and the radius, and it is increasing. And so radius is increasing, that means dr dt is changing. Okay, the radius is changing with respect to time at a constant rate of 3 feet per second. Okay, 3 feet per second. Okay. How rapidly is the area of the enclosed by the ripple increasing? So they want me to find, okay, how rapidly is the area of the enclosed area of the ripple changing, okay, at t is equal to 10 seconds. Alright, first of all, we're talking about a circle, so our mathematical model is x squared plus y squared is equal to r squared. Okay, that's a circle. So we're finding okay, yeah, we'll need that. We're finding dA dt, so we need to find the area of a circle, which is area is equal to pi r squared. Okay, so we're going to take the derivative of this. Let's see if we need this or not. We might not need that at all. Okay, so let's find the area of this. If I take the derivative of this, I'm going to get dA dt, so I'm good to go there. If I take the derivative of this, I'm going to get dr dt, and I got to make sure that I have something for dr dt. If not, then I have to go back and use that, Pythagorean theorem or the formula for a circle to go figure that out. So right now, okay, since I have dr dt, I don't need that. Okay, oops, not that one. I'm crossing out the wrong one. So I don't need this. I don't need to worry about that. Okay, let's take the derivative of this. So this is dA dt. And then when I take the derivative, this pi is just a constant. Don't use the product rule. It's just a coefficient. It's like a number. 3, 4, 5, or 3.4. So 2 times that's going to give me 2 pi times derivative of r. Okay, 2 times 2 pi, okay, times r, times the derivative of, I'm using chain rule, derivative of r, which is dr dt. Alright, so I'm finding this, so I'm good to go there. I have this, I'm good to go there, but I have a problem, which is r. I don't know what that is. Alright, so we do know the radius is increasing 3 foot per second. So after 10 seconds, at 10 seconds, it's going to be 3 times 10, which is 30 feet. So that means at 10 seconds, r is going to be 30 feet. So we're going to plug everything in now. So dA dt is equal to 2 pi times 30 times dr dt, which is 3, which is going to give me 90 times 2, which is 180 pi dA dt. Okay, and this is feet, this is the area, squared per second. So you always have to end, okay, you always have to end all word problems with a short sentence. So you have to say changing. Okay, area is changing at 180 pi foot squared per second. And that's it. That's all your short sentences. Alright, let's do one more. Okay, let's do 17. And then tomorrow we'll get to the hard ones. 17 on 224. So in 17, you have a 17-foot ladder. Okay, is leaning against the wall. So let's create a wall, and let's call this our ladder, and that's 17 foot. Okay. All right. If the bottom of the ladder is pulled along the ground away from the wall, so we'll call this side X, and we'll call this side Y. Okay, that means if this ladder here is pulled away from the wall, so it goes that direction, that means dx dt is, so dx dt is changing. If it's pulled away, it's getting positive, means it's getting bigger, so that means your dx dt has to be positive 5 feet per second. Okay, or no, it's 2 feet per second. I'm doing 16, so I can't do that. 2 feet per second. So let's change that. So 2 feet per second. No. It's 5 feet per second. Okay, 5 feet per second. How fast will the top of the ladder be moving down? So they want me to find, okay, dy dt, the change in this, because obviously that's going to be going down. Change in dy dt. Okay. How fast is the foot of the bottom moving away? How fast is the top of the ladder moving down when the wall, down the wall when it is 8 feet above the ground? So okay, when y is equal to 8 feet. Okay. So what kind of mathematical model can we use? Obviously this is going to be a Pythagorean theorem. X squared plus y squared is equal to 17 squared. We can put the 17 in, okay, because it's a constant and we don't have to say x squared plus y squared is equal to r squared or anything like that. Right. We're going to take the derivative of this. Before you take a derivative, stop and think, okay? When I take the derivative of this, I'm going to get dx dt. Do I have the information for that? Yes, I do. But I'm also going to get an x. Do I have information for that? No, I don't. So we might as well go ahead and find x. Okay, so we know this to be 8 feet. Okay, so when it's 8 feet, we've got to find out what this is. So we're going to use the Pythagorean theorem. So x squared plus y squared is equal to z squared. So we're going to put in x squared, which happens to be something we're looking for. Y squared is 8 squared is equal to 17 squared. Okay, so x squared plus 64 plus equal to, okay, 17 squared. So 17 times 17, okay, that turns out to be 289. 289, and we're going to subtract. Okay, so x squared is going to be 2, 5, and x is square root of 225, which happens to be 15. Okay? Alright, so this is 15. Okay, now we have that. Now when I take the derivative of this, I haven't taken it yet, but when I take the derivative of that, I'm going to get dy dt. Well, that's okay because I'm trying to find that. And I need to know what y is, and that's okay because I have that. That's 8. Okay? And so let's go ahead and do it. So I have a 2x dx dt plus 2y dy dt is equal to the derivative of that is constant. That's a 0 since it's a constant. We're going to plug in everything we have. 2 times x, we found that to be 15, dx dt, which is 5, okay, plus 2 times y, which is 8, and dy dt is what we're trying to find, okay, is equal to 0. Alright, 2 times 15, okay, or 2 times 5 is 10, 10 times 15 is 150, plus 2 times 8 is 16, dy dt is equal to 0. So my dy dt turns out to be over 16. Okay, and that is going to be, you have to put that in term, you got to put the units in. Okay, so that is changing feet per second. Okay, single units because it's the distance. Obviously it's going down, so that's why you get a negative answer. Alright, like I said, you have to end everything with a short sentence, and the question was, how fast will the top of the ladder moving down? So top of the ladder changing, so you're going to say top of the ladder. Okay, so the top of the ladder is changing at negative 150 16th feet per second. Okay, you do not have to reduce. Okay, but I actually don't like to write like this, so I want to get you on this. I might as well do it right. So you shouldn't write fractions like that. Okay, this is really